Hi everyone. This is lesson 1.3.1, and in this lesson we're going to be talking about combinations with restrictions. Now, in the same way that we began identifying the restrictions in permutation questions, we're going to do the same thing with combinations. However, in many cases the onus will be on you to determine whether or not this is a combination or a permutation. So just remember that questions which require combinations are going to be worded such that the number of possibilities does not depend on a change in the order of the objects being discussed. And one last note before we start working through problems. Remember that when you're working through a problem, in most cases, the sum of the numbers that occur on the left side of the combinations should be the total number of objects you're choosing from. Okay, so the numbers on the left-hand side of the combination notation and the numbers on the right-hand side of the combination notation, they should sum up to the number of objects that you're choosing. That is almost always the case, however, not always the case. So you just got to pay attention. So here's our first example. If a class of 40 students needs to choose a committee of 3 people, how many ways can this be done if the committee has a chair, a vice chair, and a treasurer? Now notice immediately that this is not a combination problem, and in fact it is a permutation. And that's one of the things that we're going to expect you to do. As soon as we've identified position, this is not a combination problem. You need to be on the lookout for that. Anytime that you have specific positions that you need to fill, it is a permutation. And so all we have to do is identify the number of options in each position and then find their product. So to begin, we note that there are 40 choices for the chair, followed by 39 choices for the vice chair, and finally 38 choices for the treasurer, for a total of 59,280 different committees. Now let's consider the same scenario here with the 40 students, but what if the committee has no designated positions? Since there is no mention of position in this question, it is definitely just a combination question. Order won't make a difference in this case. So there are 40 people on the committee, and we only need to choose 3. So we get 40 choose 3, and that gives us a total of 9,880 different committees. Now consider the following example. If there are 12 teams in a comedy improv competition, how many games would need to be scheduled so that, well, excuse the spelling mistake, so that each team goes up against every other team once? Now, to understand this question, we need to know whether it's a combination or a permutation. And in this case, when you're playing another team, order doesn't matter, and so this is definitely a combination question. And with that in mind, we know that there are 12 teams that are competing, but for any specific competition, we only need 2. Since order doesn't matter, we're going to write 12 choose 2 for a total of 66 different games that need to be scheduled. Now let's take a look at a couple of problems that are just strictly algebraic in nature. So we're going to solve each of the following for n. The first one we're going to look at here is the equation 12 choose n is equal to 495. Now in a situation like this, if you were to attempt this algebraically, strictly speaking algebraically, and you were to rewrite this in terms of factorials, you'd notice right away that simplifying would be very, very difficult. In fact, impossible, because it's hard to say where to stop the factorials. When the variable is on the, and it should say right-hand side of the combination, sorry about that, the best approach is to enter this in your graphing calculator and look at the table of values. So to do this, press y equals on your calculator, and in the y1 section there, just enter 12 choose x. Once you've done that, press second graph to access the table of values, and then all you're doing is you're looking for the line in which the y1 has the number 495 in it. And it's crucially important to notice that for both values x equals 4 and x equals 8, the result is 495. There are 2 solutions to this problem. And so this question illustrates the fact that NCR is equivalent to NCn minus R. So thus, in a question where the variable is on the right-hand side of the combination, you can expect to get 2 possible solutions. To help understand why the math works this way, it might help to think of this in a different context. Think of it in terms of asking for volunteers. Suppose you need to choose 3 people from a group of 10 to help you with some projects, whatever it is that you're doing here. You would probably use 10 choose 3 because order isn't necessarily important. However, you need to note that you can get the exact same result by choosing to ignore 7 of the 10 as opposed to choosing to take 3 of the 10. In any case, however you want to look at it, we can conclude that 10 choose 3 is going to be equivalent to 10 choose 7. Now let's take a look at another algebraic problem. This time it's going to be n choose 3 is equal to 84. And notice in this case that the n is on the left-hand side of the combination. Now, in this case, because the combination value is larger than 2, because it's n choose 3, and that number 3 is larger than 2, the expectation here is that you're going to use your graphing calculator to solve it, as you did in the previous question. Now, I'm going to show you in a little while here that there's another way around this problem here that's more algebraic, but this is the intention. So, once again, press y equals, and in y1 you're going to enter x choose 3. Then we press second graph to access our table of values, and then we're just going to look down the column, the y1 column, and we're looking for the right-hand side of the equation. In this case, that's 84. And note that in this case, the solution is 9. We can, however, approach the same problem in another way that is primarily algebraic. The first thing we're going to need to do here is rewrite the combination in factorial notation and then simplify. So we start with n choose 3 is equal to 84, and then we rewrite the combination as n factorial divided by n minus 3 factorial times 3 factorial. And then because n is larger than n minus 3, we're going to expand the n factorial as n times n minus 1 times n minus 2, and then to n minus 3 factorial. So now I've got common factors, numerator, denominator. And now a couple of things can happen in this step. First of all, we are going to cancel the n minus 3 factorials that we see in the numerator and denominator. But additionally, we're going to multiply both sides by 6, or 3 factorial, so that we completely eliminate the denominator from this problem. And we're left with n times n minus 1 times n minus 2 is equal to 504. Now, you could expand this out. Okay, multiply out those 3 factors on the left-hand side, bring the 504 over, set it equal to 0, and then try to solve the resulting cubic. That's going to be quite challenging. The easier thing to do at this point here is notice that on the left-hand side of the equation, you've got n times n minus 1 times n minus 2, and these are 3 consecutive integers. So what you're looking for are 3 consecutive integers whose product is 504. The largest one of those factors is going to be n. And after a little bit of exploration, you're going to see that 504 is 9 times 8 times 7, and thus you conclude that n is equal to 9. And it's just a little bit quicker to think of it in those terms. Now let's consider another question here. N choose 5 is equal to n permute 7 over 7 factorial. Now there is absolutely nothing wrong with rewriting both the combination and permutation in terms of factorials to simplify this problem. In fact, there's also nothing wrong with entering both sides of this equation into your calculator using x as the variable and checking your table of values. But the whole point of this question was to illustrate this equation that NCR is equivalent to NPR over R factorial. In other words, a combination is just a permutation where you divide out the number of ways you can order your choice. So in this particular question, notice that the right-hand side, the NP7 over 7 factorial, could actually be rewritten as NC7. And so we get the equation now, or we can rewrite the equation as NC5 is equal to NC7. And based on the work that we did a couple questions ago, we know that these two combinations will be equal so long as n is the sum of those two numbers on the right-hand side. So as long as n is equal to 5 plus 7 or 12, those two combinations will be equal. And finally, one more question in this format. Take a look at 3 times n minus 1 choose 3 is equivalent to n choose 5, and we want to solve for n. Okay, this question is going to require a little bit of work here. There's really no shortcut to it, not in this case. We're going to have to rewrite the combinations as factorials and then simplify the resulting expressions. So we start with our question. 3 times n minus 1 choose 3 is equal to n choose 5. We're going to write the combinations as factorials. Now, you got to be careful in this case. Think of a combination as left side choose right side is equal to left side factorial over left side minus right side factorial, right side factorial. The reason I say it like that is this is why we're getting 3 times n minus 1 factorial over, and here's the part that confuses people, it's the n minus 1 minus 3 factorial, 3 factorial. And then the right-hand side usually doesn't throw people off. That's just a straightforward application of the equation. And now we'll do just a little bit of simplifying. Notice on the left-hand side, we're going to have a 3 over a 3 factorial, which is just going to give us 2 in the denominator. The n minus 1 minus 3 is n minus 4. And on the right-hand side, all I've really done is evaluated the 5 factorial. And now we'll start the process of simplifying by working on the left-hand side first. We're going to expand the n minus 1 factorial because it's larger than n minus 4 factorial. And we'll expand it by going n minus 1, n minus 2, n minus 3, until we find the n minus 4 factorial. Then we'll cancel the n minus 4 factorials and focus our attention on the right-hand side, where we see that n factorial is going to be larger than n minus 5 factorial. So you can kind of fill in the blanks there. We're going to expand that out as n minus 1, all the way to n minus 5 factorial. And then we can cancel the n minus 5 factorials. But we can actually cancel a lot more than that because there's a common n minus 1 on both sides, an n minus 2, and an n minus 3. And so we're going to be left with, on the left-hand side, just a 1/2. And on the right-hand side in the numerator, we're going to be left with just n and n minus 4. And then I'll multiply both sides of the equation by 120 to get 60 is equal to n squared minus 4n. I just expanded out the numerator there. And then because the result is just a quadratic, I'll bring all the terms over to the right-hand side so that the whole thing's equal to 0. And when you factor the resulting quadratic, you'll get n minus 10 times n plus 6, giving us solutions of 10 and negative 6. But since our solutions have to be positive integers in this particular chapter, we know that the solution can only be 10. Now this next example is a really common question that gets asked. If a polygon has 8 sides, how many diagonals does it have? And then the hint that we're going to give here is that the number of diagonals in a polygon is always going to be n choose 2 minus n, where n is the number of sides. So solving this problem is really just a matter of substituting in 8 for n and evaluating. Thus d equals 8 choose 2 minus 8, which becomes 28 minus 8, or 20. So we can tell that there will be 20 diagonals in a polygon with 8 sides. This next question is similar, but the emphasis is in a different location. What if we know that the polygon has 90 diagonals? Then how many sides does it have? We're going to use the same equation here. So in this case, we substitute 90 in for d, and then we're going to solve for n. And because in this equation we get n choose 2, it's just 2, this is going to end up becoming a quadratic. And so the expectation is that you can solve this one algebraically. So we start with 90 equals n choose 2 minus n. We then rewrite the combination in factorial notation as n factorial over n minus 2 factorial times 2 factorial. Don't forget about the minus n at the end. Then because n is larger than n minus 2, we'll expand n factorial to get n times n minus 1 times n minus 2 factorial. And we'll also evaluate the 2 factorial, which is just 2. And in this next step, all we were going to do here is cancel the n minus 2 factorials. So we're left with n times n minus 1 over 2 minus n. Now this next step is hands down the most common place to make mistakes. I'm going to simplify the rational here by multiplying everything through by 2. So I'll get 180 on the left-hand side, but the 2 will cancel in the rational here, so I'm just left with n times n minus 1. The most common mistake is to forget to multiply that term with just an n by the 2 as well. Please remember to multiply every term in this expression by 2. Now at this point I can clearly see the quadratic popping out, so I'm going to multiply out the n times n minus 1, combine like terms, and bring the 180 over so that it's equal to 0. And then we factor the quadratic to get n minus 15 times n plus 12 is equal to 0, which gives us the results 15 and negative 12. And then again, since we're looking for just the positive solutions, we know that the only answer here is 15. And so we can conclude that a polygon with 90 diagonals has 15 sides. Okay, this next question, although it looks different than the previous one, is actually very, very closely related in terms of the math. At a family reunion, everyone gives everyone else a hug. If there were a total of 595 hugs, how many people were at the reunion? So we got to build an equation. Now, since order doesn't matter when we group people together for a hug, this is going to be a combination question. And additionally, we only need 2 people for a hug. Well, okay, I know you can have group hugs and whatever, but 2 people for a hug. And the unknown in this case is the number of people that we're starting with. So the equation must be n choose 2 is equal to 595. And to solve this, we simply need to rewrite the combination in factorial notation, which will make this one a little bit simpler than the one that we did previously. So we start with n choose 2 is equal to 595, which, as before, can be rewritten as n factorial over n minus 2 factorial equals 595. And then once again, because n is larger than n minus 2, we'll expand the n factorial to get n times n minus 1 times the n minus 2 factorial that we were looking for. And now in this step, we're going to do a couple of things. We are going to simplify by canceling the n minus 2 over the n minus 2 factorials, but we're also going to multiply both sides by 2 to remove the rational part of this problem to get n times n minus 1 is equal to 1,190. Now we expand the term on the left and then bring the 1190 over to get the quadratic n squared minus n minus 1190 equals 0. And although this one might be a little hard to factor, you can still use the quadratic formula if you needed to, but you're going to get n minus 35 times n plus 34 is equal to 0, which gives us the solutions 35 and negative 34. And again, we don't allow the negative values, so the answer is 35. There were 35 people at this family reunion. Okay, now we're going to change gears for a little bit here. You really need to see this question. Given 8 consonants and 5 vowels, how many 5-letter arrangements can be made if each one consists of 3 different consonants and 2 different vowels? And this is a very interesting question because on the face of it, it looks like a permutation. Because as soon as you start talking about the order of letters to form words, well, we know order is important. However, it doesn't work to write 8p3 times 5p2 because when you do that, you're not mixing the letters together. You're leaving the consonants at the front and the vowels at the end. They're not being mixed up. In fact, what we need here is a solution that obtains the letters first without consideration of order and then permutes them afterwards, which is why this is in the combination section. So the first thing we're going to do is choose 5 of the 8 consonants. So we use 8, choose 5. Then we're going to choose 2 of the 3 vowels. So it's going to be 3, choose 2. And we multiply these together because these both have to happen. There's an and situation happening here. And now that we've got our letters without any consideration to order, now we're going to multiply it by the number of permutation of those 5 letters, 5 factorial, for a total of 20,160 different letter arrangements. Now we're going to finish this lesson with a question about committees. We're going to look at committee questions from different angles here. A committee consists of 4 people, and it's going to be selected from a group which consists of 9 men and 6 women. How many ways can we do this? And we're going to start off with just no restrictions. Well, with no restrictions on the composition of the committee, the solution is pretty straightforward. There are 15 people from which to choose, and we only need 4. So the number of committees is 15 choose 4, or 1,365. Okay, now let's throw a restriction on it. How many ways can we make this committee if we're going to have exactly 3 women on it? Now to answer this question, you have to consider what isn't being said as well. Since there are exactly 3 women on the committee, you have to conclude that there must also be exactly 1 man on the committee, even though that's not stated overtly. So the total number of committees is the product of the number of ways we can choose the women, which will be 6 choose 3, and the number of ways we can choose the men, which is going to be 9 choose 1, for a total of 180 different committees. Now let's change the question a little bit. How many committees can we come up with that have no men on them? If there are no men on the committee, then the committee is all women. Thus, we only need to choose 4 out of the 6 women, so 6 choose 4. However, it is often useful to put a placeholder in here to identify the choice of men, even though there were none chosen. So we might write 6 choose 4 times 9 choose 0, just to include the men. And that way we know that we've got 6 plus 9, or 15 people we're choosing from, and 4 plus 0, and 4 people that we're choosing. Whether you choose the placeholder or not, there are 15 committees possible that have no men on them. This next question is related to the one that we just did. How many committees can we form that have at least 1 man on it? I see a question like this is best answered by using its complement. And in this case, the complement, or the opposite of at least 1 man, is no men. So what we do is we start with the total number of 4-person committees that are possible without restriction, which is 15 choose 4. And we subtract from that the number of committees with no men on it, which we just found out was 6 choose 4 times 9 choose 0, which gives us a total of 1,350 different committees that have at least 1 man on it. But it is possible to build this solution simply from scratch here. What we're going to do is we're going to identify the possible number of committees that have 1 man, which would be 9 choose 1 times 6 choose 3, because we have to have 3 women on it, or 2 men, and so we're going to add 9 choose 2, so 2 men, times 6 choose 2, or 2 women, or 3 men, and so we have 9 choose 3 times 6 choose 1 for the 1 woman, or 4 men, and so we add 9 choose 4 times 6 choose 0, representing the choice of no women. And once again, for a total of 1,350 different committees. And you might choose this method because it's a little bit easier to see exactly what the committees are composed of at each step. And here's another variation on the problem. How many committees can we come up with that have at least 3 women? The best way to answer this problem is to simply build this one scenario at a time here. And the reason I say that is because I've watched students assume something about this problem that wasn't true. The best advice I can give you here is that as you're building the combinations, when you're multiplying them together, if the first 2 numbers don't add up to 15, which is the total number of people you're choosing from, you're very likely doing this wrong. So let's start by choosing 3 women and 1 man, and adding to that the number of committees that have 4 women and no men. And I do apologize for this. That symbol there should be a plus sign in between the 9 choose 1 and 6 choose 4. They should be added together for a total of 195 committees. Now we're going to take a look at just a couple more questions dealing with specific choices here. What if Al and Barry cannot both be on the committee? It's important that you understand what's being stated here. When they say that they cannot both be on the committee, the implication is that either one of them is on the committee, which would be 2 choose 1 times 13 choose 3 to fill in the rest of the committee, or neither of them is on the committee, in which case we would write that as 2 choose 0 plus 13, and I'm sorry, once again, that should be 13 choose 4 to be choosing the whole committee, for a total of 1,287 different committees. Again, remember that's 2 choose 1 times 13 choose 3 plus 2 choose 0 times 13 choose 4. Now let's take a look at the same question, but in a different direction here. What if Alana or Barbara must be on the committee? This one is more positive than the other one. Once again, we need to be very clear on what the word or implies here. It means either one of the women is on the committee, in which case we would do 2 choose 1 times 13 choose 3 for the remainder of the people on the committee, or both of them are on the committee, in which case we would write this as 2 choose 2, we're choosing both of them, times 13 choose 2 to choose the remaining 2 people for the committee, for a total of 650 different committees. Now finally our last question here. How many ways can we choose the committees where Lucas must be on the committee? Now this question worded in this way can be confusing for some people. It's important to note that in this situation, to choose Lucas, you would not use 9 choose 1, because that is simply going to be the number of ways of choosing a man. Not a specific man, just one of the 9 men. So we use 1 choose 1 to choose Lucas because there is only one Lucas to choose from. And so the expression we write is 1 choose 1 times 14 choose 3, because we need to find 3 other people to finish the committee, for a total of 364 different committees.